Okay, shall we make a start? I'm Peter Pauli, head of mechanical engineering here. Very warm welcome to all of you, particularly the visitors. Inaugurals are great occasions because it's an opportunity to celebrate achievement. This one is an unusual one for us in that most of our chairs are promoted internally. David is an externally appointed chair, which is a very nice change from the custom. David's CV tells me that he did engineering at Cambridge, and then he did a production engineering master's, and then he worked for British Rail for 3 years, and then he went to do a DPhil at Oxford, and then he stayed there for 30 years. And takes some people longer than others to see the light, but 2 years ago he saw the light and decided that Imperial is clearly the place to be. So here he is, and a very warm welcome, obviously, to David for coming here. Our immediate reason for recruiting him was to run the vibration Rolls-Royce UTC, and part of David's career at Oxford was running the solid mechanics UTC. So he was a rather obvious recruit for us with that sort of experience. But David's got very wide interests in solid mechanics generally, and fatigue, friction, wear, structural integrity, hence the title of his lecture. So David, we look forward to hearing it. Over to you.
Well, thank you very much, Peter, and it's an enormous pleasure for me to be here. In some ways, it's quite a surprise to be here. I'm not sure if I'm quite the oldest person ever to have given an inaugural lecture, but I'm certainly at that end of the distribution. As Peter said, you know, my career has sort of gone around the so-called golden triangle, and finishing up at the third vertex at my stage in the career is a very great privilege for me. And I'd first of all like to thank Peter and all my colleagues here at Imperial for the very warm welcome that they've given me since my arrival. So, it doesn't seem very long, and indeed I was talking to my predecessor this afternoon. It doesn't seem very long since I was at my predecessor's inaugural and I was sitting where you were sitting. And he had a very, very snappy title. And I spent a long time trying to think of a snappy title that would, and in the end I've sort of given up. In fact, this was going to be Leonardo and the Dreamliner, but those of you from Rolls-Royce will realise why that's not a good idea to talk about at the moment. So it's Leonardo and the A380, and I hope by the end of the lecture you'll see why Leonardo's got something to do with the A380, and the kind of research that I'm interested in, and why Imperial is a good place to come and do it. So without further ado, there is an A380, and it's a huge and sophisticated aircraft. If you've flown on it, it's a very quiet aircraft. It's a very nice aircraft to fly on. The time I went on it, I went business class. Somebody else was paying, so that was even nicer. But the thing that most people don't realise about the Airbus A380 is that the clever bits are the wings and the engines, and both of those are made in the UK, or at least some of the engines are made in the UK. All of the wings are made at Broughton in Cheshire, and indeed, you know, Airbus are fond of saying half the world flies on wings made in Broughton, and I think that's pretty much true. So don't let anybody tell you that mechanical engineering is dead in the UK. Now, the interesting thing about the A380 is, and I got this from Wikipedia, so I hope it's approximately correct, but it has 4 million components, which is quite a lot of things to manage to achieve to put together in approximately the right order. But the other thing is that, as we will see, the lecture is going to be concerned about how these components fit together, and indeed how we get loads from one component to another. because this thing does not behave as a rigid solid body. It's made up of different components, and in particular the engines, which we'll focus on, are an assembly of components all under loads. And basically, the loads have got to be transmitted from one component to another. So if we take these large fan blades, which are at the front of the engine here, this is the bit of the engine that you kind of see when you board the aircraft, and they are slotted into a disc, and they must be held in that disc, and they must be held successfully. And the same is true of the compressor, which is the next stage back, and the turbine, which is back here, and so on. So you can imagine that we've got a lot of loads, and then this thing has got to be mounted in a nacelle, and it's got to be bolted on the wing in such a way that A, it doesn't fall off, and B, that it transmits the thrust loads which it's developing to the airframe, because otherwise the engine is going to go off and leave the aeroplane behind, which is not a terribly good thing. And the thing about those contacts is that they actually present significant unknowns in the system. So we make our systems up from a number of different components. We've got to transmit forces at points of contact between those components. These give rise to stress concentrations, and they're frequently involved in failure, but they also present us with significant difficulties when we come and try and simulate the system on our computers. And simulation is becoming increasingly important, of course, because testing is very expensive, product cycle times are coming down. We simply don't have the luxury of building something, seeing how it behaves, and then refining it. I'm told that when you go to Dyson's place in Wiltshire, there's a sign in the entrance, and it says 1,000 prototypes to build, the first vacuum cleaner. And that might sound very impressive, but of course it would have been better if it had been one. So, building a lot of prototypes is not necessarily a good idea. So, it's fairly obvious we can't make complicated things out of a single component. We need different geometries, we've got restrictions on size, we need different materials, and fairly obviously as well, those of you who are engineers in the audience, we love taking things apart, and if it was made of one component, we wouldn't be able to take it apart, and that would, be a severe disappointment to us. But transferring a load across an interface is not easy, and it turns out to be a very complex process. Even if we take the simple case of a normal load, where we're simply transmitting pressure, it's quite difficult to design the interface without leading to concentrations of load and concentrations of stress. So, for example, if you take a flat punch and you press it down onto a surface, you might think that that would generate a uniform pressure. But in fact, what you would find is that there are stress concentrations at the edge, and indeed, if the punch is rigid, those concentrations become singularities. So pressure becomes infinite at the edge. If, on the other hand, we take something like a cylinder and we push that down, you will see that you get deformation of the two bodies, but the pressure will be largest in the middle, and it will fall to zero at the end. And it turns out that it's not possible to design an interface that carries uniform load across a range of loads, unless the two components perfectly match, and then you start to wonder why you've got two components in the first place. Okay, so that's contact mechanics. What can go wrong? Well, this is one of my favorite video clips, and I apologize to those of you who've seen it before, but you will understand why I want to show it. It was on Australian television news. Can we have some sound, please?
To dramatically abort its takeoff from Melbourne, tonight preparing to finally fly out of Australia.
Oh, I did say it would do this.
It was a frightening experience for those on board when an engine of the Emirates Airlines jet burst into flames as it rolled down the runway. One of the 213 passengers happened to be filming their farewell to Australia as the Emirates Boeing began to take off just before 9 p.m. As the flight crew accelerated the engines, they all got the fright of their lives.
A loud explosion. I actually thought a bomb had gone off on the aircraft.
There's a big flame and the jittering and the...
There we go. Well, that will actually do. The thing I learned from that is if you ever see anybody videoing out the side of the aircraft when it's taking off, just tell them to stop. It's quite extraordinary. I mean, you know, that's only happened about 3 or 4 times to Rolls-Royce engines in service, and yet, you know, somebody was filming it. And just to put it into context, that happened 2 weeks after the Concorde crash in Paris, and you can see why those people are nervous. And what has happened was that the engine lost a blade here, and you can see it's damaged the trailing blade and all the tips and so on, and there's the failure, and essentially it's a fatigue crack which has started from pretty much the edge of contact. There are a few kind of subtleties in there which we can talk about later if you wish. Here's another example. This one isn't a Rolls-Royce engine, but it's kind of much more dramatic in a way. So here the engine in flight, the same things happen, but in flight it's lost the whole of the front of the nacelle, and unfortunately a piece of that nacelle penetrated the fuselage and somebody was killed in that incident. But again, you will see this fatigue crack, and these lines here are what we call beach marks, very characteristic of fatigue failures, and the origin of this crack is from the edge of the contact, which is from here to here, where that blade was being restrained in the disc. So there's a lot that can go wrong on contact. So why do these things go wrong? Why do they fail in a way that's much less predictable than, as it were, the parts of the component which are not subject to contact? Well, to answer that question, we have to start talking about kind of tangential loading. So we've been talking so far about normal loading, where we just have pressure between the two components. Now we want to kind of see what happens when we try and move them tangentially relative to each other. So we try and, in effect, we're pushing them to see if they will slide. And that tangential loading is resisted by friction, and we're all kind of fairly familiar with friction. I remember as a child, my parents bought an encyclopedia, and this was all before internet and before Wikipedia and so on, and one of the pages that fascinated me was a page which said, you know, what would happen if there were no friction in the world. And it had various kind of diagrams of locomotives crashing and various things. And of course, we do experience it ourselves, because if you try and ride your bicycle on an icy morning, which I do on occasions, particularly now that I have to get to the station in a hurry, and you come round a corner and there's an icy puddle, you will experience what the world would be like without friction, and it's a jolly dangerous place. Anyway, as engineers, we often think of friction as a nuisance, and in some senses it is a nuisance. If we're running an engine, for example, we want to reduce friction, but if we're designing brakes, then actually we're relying on friction. And indeed, if we're designing an aircraft engine, we're relying on friction to hold it together. Even something as simple as a nut and a bolt would not work without friction. And you probably remember back at school doing little experiments with a wooden block, you know, and you put one block of wood on a plank and you lift it up, and at some point it slides, and then you have to work out the forces and work out the friction force and what the coefficient of friction is. Where does this come from? Well, when you read the literature, people will call this Coulomb friction. And in fact, Ken Johnson, who was, you know, the Mr. Contact Mechanics, used to say, well, actually, it's not Coulomb friction at all, it's Amundsen friction. Because the so-called laws of friction, as we know them, appear to date back to Amundsen, who published a paper in 1699. And what Hamilton said was, frictional force is independent of the apparent area of contact. So if you take a brick and you put it on, as it were, each of its sides and try and slide it, the force will be exactly the same. And similarly, he also said that force is proportional to, the frictional force is proportional to the normal force, so you get this simple equation, F equals mu p, where mu is known as the coefficient of friction. And if you do this experiment with a block of wood, you get the answer that mu is about 0.3. So that tends to be the figure that people have in mind, and it's amazing when you start talking to people with, as it were, problems in contact, and they may have not put any friction in at all, or they may have put some in, and if they put some in, you say to them, what coefficient of friction did you use? And they will say 0.3. And you say, where did you get that from? And they said, well, it's kind of seemed about right. And often they're kind of thinking back to that school experiment. And in fact, what we will see is that with metals, on metals, the coefficient of friction is kind of anything but 0.3. And then about a century later, Coulomb comes along and says that frictional force is independent of sliding velocity. And none of these three statements are completely correct, but of the three, that one is the least correct. So the message is absolutely clear. If you want your name associated with a phenomenon forevermore, find out a couple of things that somebody said which are right, add something that's wrong to them, and that's where you go. But in fact, more recently people have discovered that actually Leonardo da Vinci was studying friction a couple of hundred years before. And, you know, these are some of Leonardo da Vinci's beautiful sketches from his notebook. I mean, don't you all wish that your students kind of sketch the apparatus like that? And what his experiments show and his notes show that he had a good basic understanding of these 2 points, that the areas in contact have no effect, and the load of an object is, if the load of an object is doubled, the friction will also be doubled. So he knew what Hamilton knew, and he knew it 200 years before Newton defined what a force was. And I think that's quite extraordinary. You know, we think of Leonardo as being quite extraordinary in a number of ways, but Da Vinci knew about experiments. He was able to determine what was going on between two sliding interfaces, and yet there was no formal definition of a force. Now, the first of these is, to some extent, rather counterintuitive. If you ask an undergraduate, why do racing cars have big fat tyres? Most undergraduates will say, well, it's to get more grip in the corners. And of course, most undergraduates would be absolutely right. That's why racing cars have big fat tyres. And then you say, how does the frictional force vary with the area of contact? And they say, well, Coulomb's laws tell you that it's independent of the area of contact. So then you say, why do racing cars have big fat tyres? And it's very surprising how people can carry these two contradictory, as it were, facts in their minds and yet not see the contradiction. And the answer to the conundrum, of course, is that rubber is not a Coulomb friction, is not a Coulomb material. And indeed, these so-called laws of Coulomb are not the same as some of the other laws of applied mechanics, which we're going to come on to. So, why did I start getting interested in this? Well, one of the reasons was, following that kind of incident in Melbourne and various other things that were going on, we got involved with doing some test work on these kind of features up here, which are essentially representing how we fix the blade in the root, in the disc. And you can see here these cracks which are developed from that contact. And we came to the conclusion that really you wanted to do one of two things. You wanted either to make the friction zero, and in that case there's no problem, or you want to make it infinite, in which case the two things are stuck together and you might as well be one component, and therefore the problem's gone away. Unfortunately, we had not thought about where the loading was coming from. And the loading's coming from vibration, and as far as the vibration perspective is concerned, you want the friction to be anything but infinite or zero. You want it to be somewhere in between those two things. And so you have to look at this problem, you have to start looking at it holistically. You have to start to understand the solid mechanics, the contact mechanics, the tribology, which is what's happening at the surfaces, and the dynamics of what's going on. So let's say something about dynamics. And many of you will have come across this equation in one form or other. It's probably the most important equation in applied mechanics. And I like it for a number of reasons. I like it because it's so simple. It's, for the mathematicians amongst you, it's obviously a second-order linear differential equation. That's fine. But what you've got in here is a couple of things from the greats, really, of applied mechanics. So what we have here is a force, and typically we think of a periodic force, so something that's varying with time. And first of all, we have a term which is stiffness times displacement. So, and the man who figured this out was Robert Hooke, who said that force is equal to stiffness times displacement. So that when you apply a force to something, it bends or it displaces out the way, and at least to start with, that force that you get is proportional to the displacement. And then here you get the Newton, and what Newton said is force is equal to mass times acceleration, or effectively that. And then here we've got the term that goes in the middle, and this is the one that we're going to talk about, is force equals a damping constant times the velocity. Now, we've got here a picture of Newton. Newton was a Cambridge man, of course. Robert Hooke was an Oxford man. It would be tempting to say that this came from Imperial, but I'm afraid Imperial weren't around at that time. The portrait of Hooke, of course, is not an original one. It's not a great portrait in many ways, but I like it because this view out the window is pretty much the view that I had from my college room in Oxford. Sadly, I had to give that up to come here, but anyway, that's another story. And the thing about Newton and Hooke is they hated each other. They absolutely could not stand each other. And Hooke had the misfortune to die earlier than Newton, and they were perennially fighting over who'd thought of what first. And Newton pretty much erased all that there was in the Royal Society relating to Hooke. So there are no extant, as it were, contemporaneous, portraits of Hooke. The other thing that's interesting about Hooke, so they both were sons of clergymen, but Newton came from a fairly wealthy background, and Hooke came from a very poor background, and in fact his father died when he was very young. And Hooke actually was a servitor at Christ Church, which meant that he paid for his studies by serving the richer students. And one does sometimes wonder whether, as it were, student funding mechanisms are not going in the same way at the moment. But I won't get into that. Okay, so there's the equation. What's the consequence of that equation? Well, the consequence of that equation is found when we try and excite a system at different frequencies. So basically what we're doing is we're taking a force here and we're varying it, and we'll vary it very slowly to start with, and then we gradually increase the frequency of that force. And what happens is if we vary that force very slowly, then the acceleration is extremely slow, the mass term doesn't matter, and all we get is that the force is resisted by the spring. So what we have is a stiffness-controlled response, which is static. On the other hand, if we vary that force very quickly, then the acceleration is very large, and so that the mass times acceleration term dominates, and we get this behavior here, where the faster we vary the force, the smaller the size of the response in terms of the displacement. So that's fine. Unfortunately, to get from here to here, we have to go through this phenomenon of resonance. And this phenomenon of resonance is where the system is extracting maximum energy from the force, and if we don't have any damping, the amplitude of the response will become infinite. And if we have some damping, then that will reduce the amplitude of that response. So this is a really bad place to operate your system. Now, unfortunately, our real systems, this is what we call a 1 degree of freedom system, so it has a single mass and a single stiffness, and that's fine. It has one resonant frequency, and we can usually avoid it. But if we take a complex system like an aircraft engine, it has multiple, in fact, it has infinite resonant frequencies. Fortunately, some of them are so high we don't need to worry about them. And so it's going to be quite difficult to avoid all of them, particularly when we realize that we have to operate the engine at different speeds. And the effect of exciting vibration close to its natural frequency can be quite unfortunate. Now, the last inaugural I went to by my colleague Guillermo Rein, he studies fire, and he had a really nice demonstration here of a kind of whirlwind fire thing. And I thought it would be great to have a demo. But when I consulted the safety officer, she wasn't very keen on this. So I'm afraid you're going to have to make do with the video. There's a lot of these on YouTube, and they're great fun. So I do, you know. Oh dear. Yeah. So that's what happens when you put a brick in the washing machine. So don't try it at home. But actually, seriously, you've actually all seen this in the kitchen or utility room, because you put your wet towels in the washing machine like this, and the system is so configured so that it's operating up here. But to get from here to here, it has to go through the resonance of the system, and that's when it starts bouncing around. And as I've tried to explain to various members of my family on several occasions, if you put too much in there, it will spend a long time in this region here, and that will be when the amplitude of vibration builds up and it starts walking across the floor. But somehow they don't always take my advice. Anyway. More seriously, different frequencies excite the system in different ways, and this is quite a nice little demonstration. So we have a flat plate here and some salt, and we're shaking it up and down in the middle, and we're shaking it at different speeds. And what will happen, no one stopped as well, is that you will see that the salt kind of walks around until it gets to what we call the nodes in the system. So these are the places where the plate is not moving, and in the middle are the places where it's moving up and down. And look at the beautiful patterns that you get. You know, isn't applied mechanics a wonderful thing? You know, I sometimes think that we should have an applied mechanics art show, and you could sell this stuff for millions, and we'd all be a lot richer. Okay. So why is friction so important? Well, friction is important because actually in most structures, that's where the damping comes from. The damping isn't this nice linear damping that you see in that equation. It's actually frictional damping. So for example, if you take something like this, which is a disc from an aircraft engine, and it's got lots of blades in it, that is kind of reasonably well behaved. It's not perfectly well behaved, but it's reasonably well behaved. Why is that well behaved? Well, because it's got lots of joints where the blades fit into the disc, and what that means is that it's got quite a bit of damping. Now, it's become fashionable, and you can see why, to take this kind of system and replace it with this. This is what's called a blisk, or a bladed disc, where the blades are, in effect, attached to that component. There's no joints, they are integral with the component. The only problem is, this one will ring like a bell. And if you don't believe me, let's just have a think about this. So, and I think you, I don't know why So the first of those bells was cracked, and the second one wasn't. And you get a completely different response, because in the first case, the two sides of the crack will rub together, and that will absorb energy, and that will damp out the vibrations. In the second case, it's a bell, there's no cracks in it, and it rings. And indeed, you know, that's where, I don't know, some of you will be old enough perhaps to remember the wheel tappers who used to go along and bang the wheels of the railway coaches, trying to look for cracked tyres, and basically they're looking for that. If you hit one with a crack, it will sound much duller than if you hit one without a crack. Okay, so what we thought we had was this nicely behaved equation here with a damping term where the damping force behaved linearly with velocity. So it went like this. And that's a reasonable approximation for things like shock absorbers, but it's absolutely hopeless where we have friction, because what you get with friction is that Coulomb says, well, or Amonton or Leonardo or whatever, says it's constant with velocity if you're sliding in one direction, and if we slide in the other direction, it reverses sign. Now, of course, that's just the simple, as it were, one-dimensional friction, whereas in fact, of course, it can slide in any direction, and it becomes even more complicated. But frictional damping is highly nonlinear. It's about as nonlinear as we can get. So the real situation is this, and the green line is the standard model. So actually, we now need to modify the equation to look like that, and now we've got a super equation because we've got Newton in the first term, we've got Leonardo in the second, and we've got Hooke in the third. And you know, what better equation could you get to combine the greats of applied mechanics? Nonlinear damping has some very interesting effects. Firstly, of course, the equation's more difficult to solve, and don't ask me how to solve it, that's not my domain. But secondly, the response becomes non-unique, and it becomes history-dependent. So that kind of sharp peak that we had before tends to start to lean over. So here we've got the amplitude of the response, and here is our forcing frequency, how fast we're exciting the system. And that has some interesting effects, because as we increase the frequency, we go along this nice curve here, and that's fine. And we get to the top, and then the system will snap down to here and behave like that. And then if we come back in the other direction, we'll come up to here, and then the system will snap up to there. And in fact, we never get this dotted response at all. And whether we are up here or down here depends in which direction we've approached it. And you can even get more exotic responses. I mean, even a system like this, which is a mass with some friction and a force, and you can, normally with these systems, we expect them to stop at either end of the travel, a bit like a clock pendulum. So it stopped there, and it'll stop there. With frictional systems, it can stop in the middle. And you sometimes get these kind of behavior where you get 2 stops in a cycle or multi-stops and so on. And you get a very, very complicated response out of a simple forcing function because of the nonlinear nature of the equation. Okay, so how do we measure friction? It's very difficult to measure it without sliding the whole contact. It's not impossible, and again, I can fill you in on that later if you're interested. But what the tribologists do, those who study friction, is they do what's called a pin-on-disc test. And you can see why they do this. It's nice and simple. You put a pin on a disc and you rotate the disc and you measure the force. Well, fine. But the trouble is here, we've got a very, very different system from what we've got in most of the joints in the engine. Here we've got a sliding contact. We've got temperatures going to build up. We've got wear particles which will be exposed, and so we'll have a very, very different development of friction. So this isn't a good test. And indeed, the kind of tests that we like to do, which are more representative, is to slide the contact a small amount in each direction. So we, in effect, take, say, a specimen, grip it with some pads, and we move the two relative to each other. And the kind of thing that you get is this kind of curve, and it's got some interesting features. The first thing that you can see is that you've got a region between here and here where there's sliding at an approximately constant force. And that's the region where we have Coulomb friction or Hamilton friction taking place. But you'll see here it's only approximately constant. And then we have a phenomenon here where if the contact were, as it were, perfectly stiff, then we would simply have a rectangle here, but in fact we've got a slope on there. And this is due to some compliance in the contact, and I want to explore in the remains of the lecture what that compliance results from and why it's of interest to us. What you find if you do those kind of loops is that the coefficient of friction that you get to them kind of increases quite dramatically to start with, and then perhaps a bit more slowly. Almost certainly what's going on is that you've got some kind of surface cleaning taking place to start with, and then you get a gradual sort of degradation of the surface due to wear. So that what you will see, these are kind of scars, and the colors represent depth. So the blue is a deep spot, and the red is high spots. And you get material transferred from one surface to another, and the surfaces change quite considerably from how they were when you started the experiment. And this is going on all the time in our engineering systems, and yet we very rarely take account of it. The other thing is you might like to think that friction was kind of at least constant. Well, what we've got here are four contacts, 1, 2, 3, and 4. You'll see them a bit more clearly in a moment. And this is an experiment where we're vibrating these blades and measuring the heat, or measuring the temperature, in fact, of so we're in effect measuring heat generation. Now what you'll see is that this contact here is hardly doing anything. So that's got high friction and it's not slipping. This one down here is generating a lot of heat, and that's got low friction and it's slipping a lot. And so you get, even with four notionally identical contacts, you get very, very different behavior. And small differences in friction can make a very big difference. So, for example, it's quite clear that, this one is stuck and this one is sliding. If the friction had been slightly the other way around, it would have changed that result. Surfaces aren't flat. You can tell that, obviously, and take any surface, you run your fingernail over it, you can feel that surfaces aren't flat. They have a surface roughness. And the roughness that they have depends on how they're manufactured. And we can look at these surfaces and we can generate these kind of nice maps and so on of the surface. You have to be a bit careful with these because you can run away with the idea that putting two surfaces together is like putting the Alps on top of the Pyrenees. And actually, when you look at the scales on here, you'll see that as it were, the Z scale, the vertical scale, is highly exaggerated. If you didn't do that, you wouldn't see anything. And actually putting two surfaces together is a bit like putting Cambridgeshire on top of Lincolnshire. you know, that they are pretty flat, actually. But nevertheless, they're not completely flat. And so I've been interested in surface roughness for a long time. This is, I still have my final year project report, and I was supervised by Jim Greenwood, who is kind of Mr. Surface Roughness. And it was great fun working with Jim on my final year project. We've done over the years a bit of modelling of what happens with roughness. Daniel Mulvihill, who's in the audience, will recognise these models. He put them together, and he did this rather nice simulation of, if you like, part of Cambridgeshire moving across part of Lincolnshire. So all my videos are stopping simultaneously. Anyway, so we've got one bump moving across another, and we've got this nice finite element simulation, and he's even put a failure criterion in there, and there's your wear particle. And Daniel did some very nice work at different overlaps and was able to generate estimates of the coefficient of friction. And you get some pretty reasonable answers, actually. But, of course, the trouble is we don't have the computational power to do this for realistic surfaces. Again, we had a collaborative project with Imperial some years ago, and here's some work that Simon Medina did at simulating what happens with a contact. So here you see when it's lightly loaded, there's just a few points in contact, just these high spots. And then as we increase the load, these spots expand, and more points come into contact. And actually, when you put a flat surface down on a flat surface, it comes to look like this. And you can model this phenomenon, and you can, from that, conclude that a surface, not only about the friction, but you can conclude that a surface is less stiff than it would be if it were smooth. One does calculations, and you can find that the stiffness of a surface, i.e. its kind of springiness, depends on the load. So as we push it together, more and more area comes into contact, and the surface gets stiffer. And we've got a great tool now, which has come in the last decade, called digital image correlation, that we can use to study displacements at a very, very small scale. This happens to be a crack, but again, it's a nice kind of video. There you can see the crack being loaded by a cyclic load, and then we put an overload on it. And what you can do by digital image correlation is you can take each of those images in the video and you can overlay them, and you can match up part of image 1 with image 2, and you can find out the displacement. You can get a complete displacement map. And that's really useful. We can use it in contacts. So if you look at a pair of contacts, for example, you can see that the displacement in one surface follows this line, and we would expect the displacement to be continuous. But it isn't. There's this gap across the contact. And the reason is we've got this rough layer, which is very, very compliant. It's very, very springy. And we get this gap, and from that, we can plot that gap against the force, and we can generate a curve like that. And what you can see is that the contact stiffens up. That we start here, we get a lot of displacement for a small amplitude and load, and as we go round here, we get much less displacement for our increase in load. We have studied that both at Oxford and Imperial. We've got different rigs, but essentially you get very similar results. And here's an example of, again, zooming in very much on a contact. You can see a little bit of slop in the system, but we can extract from that the kind of displacement data that we need to plot stiffness. And what we find is that contacts change. Again, so not only does the friction coefficient change, but also the stiffness of the contact changes. So you can see here we've done loading and unloading of a normal contact, and the contact changes, its response changes each cycle of loading. And almost certainly that's because the geometry is changing. And the same thing kind of happens when we try and slide contacts. So you can see here that here's the stiffness. It will decrease as we try and slide it, and eventually it will reach 0 when we're on the point of sliding. And then when we reverse the load, it'll pop back up to here and decrease and so on. But each time we do that, the contact is getting stiffer. Now, it's very difficult to do these experiments, and we haven't so far managed to do them for much more than a few cycles like that. But it's going to be interesting to see how that maps onto what happens if we run the contact for hundreds or thousands of cycles. What's the current state of modelling? So this was done by one of the students in the group here, and in fact, and with some other students on the summer school that my colleague Christoph Schringschackl organised. And what you can see here is this is actually our experimental system downstairs. Here you can see effectively this is normalised acceleration, so this is response. And if we model this system, we get this yellow curve here. If, on the other hand, we take account of how the system wears and how that changes what's going on at the interface, we get this blue model here, and that ties up much better with our experimental measurements of the system response. So that seeing how the interface develops is as important as seeing what the interface looks like when it's new. Okay, so where does this leave us with Leonardo and the A380? Well, the A380 is an extremely sophisticated aircraft. Leonardo da Vinci, of course, had ideas about aircraft design, and he had some quite interesting ideas about aircraft design. We're way beyond that in terms of our understanding of fluids and structures and so on, but this thing is essentially designed on knowledge that comes from about 500 years ago, as far as the interfaces are concerned. It's got us a long way. The giants of applied mechanics really were giants. The next generation of aircraft, I don't know whether they're going to look like this. Some people will say that they might. But we're going to need a much better understanding of what goes on between components if we are going to ensure that you continue to be safe and that we don't do too much damage to the environment. So, all sorts of things, really. This is, in some ways, a kind of technical slide. But the thing that I want to highlight here is what we need is understanding that will allow us to design joints with specific properties, joints where we will be able to predict their behavior, and joints where they will all essentially behave in a similar way. To make progress, we will need to understand solid mechanics and dynamics and tribology and structural integrity. And Imperial is really a fantastic place to do work in that area because my colleagues here have expertise in all of these areas, and we have, I think, a lot to contribute over the next 5 to 10 years or so. I'll finish with this one. Pauli had a lot of interesting things to say, but this is, I think, one that I always like to bear in mind. God created the solids, but surfaces are the work of the devil. They are fiendishly complicated, and that's why they're so interesting. And of course, I must acknowledge all those who've helped me over the years. The great joy of being an academic is that one gets to work all the time with the brightest young people of their generation. It's a fantastic privilege and one that I've enjoyed throughout my career and I continue to enjoy. Thank you very much, ladies and gentlemen.
So David, thank you very much for a most entertaining lecture, most informative lecture. It's always very nice when a new professor ends with a research agenda, particularly when his sponsors are in the audience as well. So checkbook at the ready, Soph, I think we'll find. It's now my great pleasure to ask David Hills from Oxford to propose a vote of thanks. David.
Peter. So first, it's not the tradition to have questions at the end of an inaugural, but David said he'll take a few. Are there any burning questions or anyone wants to ask? Yes, please.
Hugh Smallman from John Moores University. How do you make the bliss work if you start this horrible...
Yeah, that's a good question. There are things you can do. You can put coatings on. So it is possible to put a damping kind of coating on the outside. So a mixture of kind of ceramics and polymers, and you just effectively paint that on. The only trouble is it tends to fall off. So, I mean, there is a real issue about blisks and vibration. Yeah.
Thank you.
Anyone else?
Oh, there's one. Oh, it's Dave.
Oh, I might have guessed. Right.
So doesn't it make life a whole load easier for you when we put low friction coatings on the interfaces between the blades and the discs?
Well, yes and no. It does, but of course there can be less damping. If you go the wrong way, there can be less damping, so the forcing gets bigger. The other interesting thing, which we discovered a few years ago in sort of collaboration with people at Rolls-Royce, particularly Kash Chahal, who's not here this evening, but is that a partially worn coating is worse than no coating at all. So the trouble is you put coatings on and that's fine, but as we all know from our frying pans, coatings don't last forever, and a partially worn coating is worse than not putting a coating on at all, because the points where the coating is worn through will have higher friction and they tend to attract all the load. So it's as if you've got, as it were, hot spots throughout the contact which attract the load. So coatings have their place, but they're not always a fantastic solution. And also, it's not always great to think of yourself relying on the fact that somebody's painted this component in a particular way when you're at 30,000 feet. But yeah.
Okay, so thank you very much, David. I was a bit worried on the first slide. I thought you were going to change your profession when I saw you in the white coat.
No, they won't let us anywhere. You can't have a photograph taken in a lab without a white coat here, but...
This is the second one of these I've done within a year or so. The other one for Daniele Dini. I'm wondering if I can apply for a part-time job, please, Peter. Of course, I've been very lucky to have had both Daniele Dini and David as colleagues. Daniele can't be with us tonight. Unfortunately, he was going to come, but his baby's sick. But it was a privilege to give a vote of thanks for him. And he and I have been working together for 15 years, but that pales into insignificance compared with the third of a century that David and I have been working on things. I showed up in Oxford in '84 and made an application to the then SERC, I think it was at that stage, to do some basic work on fretting. And David applied for the job, and we got on like a house on fire. In those days, there were no such things as milestones and deliverables and management of micromanagement in EPSRC or SERC contracts. They were just trusted to get on with it. But they got tremendous value. We worked very, very well together and made good progress. And the experiments that David did virtually a third of a century ago, as I was saying, are still very much the seminal experiments in some of the basic understanding of fretting problems. Now, not only did we work together scientifically, but the work with Rolls-Royce was building up, and then we got the UTC there in Oxford, just before Imperial. Carlos Ruiz was the inaugural director of that, and got things going really, really very, very well indeed. Carlos retired, I can't remember the exact date, but it was about the turn of the millennium, left David with a bundle of trouble on a piece of apparatus, which he spent the next year working all hours putting right, and which proved very valuable to the company. And he also made David director. And I'm ashamed to say that I was slightly envious. Well, that envy lasted about 3 days before I realized that they'd picked the right man, because not only is he a fantastic scientist, but he's also a very great administrator and an organizer. So we continued to work together in that way for a while, and then David handed over the baton of the directorship to me. But that was fine, because I could just walk down the corridor and ask him when I got into trouble, and again, that was fine. And then, unfortunately, about 5 years ago, David had a bit of a health scare, but things have really, really picked up since, and I'm very, very pleased for him. It's terrific to see that he's come here, now that he and Deanie have had their training at Oxford. And now he's director again, rather, of the UTC. It means that when I get into trouble, I can just phone him up and freeload some advice, and that's really reassuring. It's good to see not only colleagues, but also friends over many years here tonight, and also family. And I nearly fell into the trap of making a sexist remark by hoping that Dr. Nowell and Mrs. Nowell Sr. had learned their lesson, but this also applies to Arthur and Peter, that I hope they remember now how to load the washing machine. Yeah? The consequences are severe. So, David, I want personally to thank you myself right now for that third of a century of scientific collaboration, which I very greatly enjoyed, some of which you've shown today, but for your personal friendship and help when I needed it, and that matters very much to me. But now I'd just like to propose a formal vote of thanks to David for giving this evening's lecture. I hope we'll show our appreciation.
Well, David, thank you very much for giving the vote of thanks. It's interesting you should ask for a part-time job here. As you should be careful what you wish for, because you may or may not know that the definition of a part-time professor is one who's only here part of the time.
Oh, right. Yeah.
Sorry, who's only, I said that wrong. Who's only away part of the time, I meant to say.
Yeah.
It helps to get jokes right, doesn't it?
Sorry, yes.
Yeah,
right,
yeah. The old ones are the best, though.
They are indeed, yes, quite. Anyway, that concludes the formal proceedings for this evening. So thank you very much for coming. And there are drinks outside if you care to join us. Thank you.
Right. Thanks, Peter. Sure.